All right, let's talk about Gibbs Free Energy. So what is the symbol, what letter do we use to represent Gibbs Free Energy? G. And I'm going to take advantage of that in a little bit because it's also the letter, a lowercase g anyways, that we use for gravity. And that's my way of kind of remembering something about Gibbs Free Energy. So Gibbs Free Energy. The big thing about Gibbs Free Energy is it allows us to predict if a reaction will be spontaneous. So in this case, the change in G tells us some things. If it's negative, that means the reaction is going to be spontaneous. And if delta G is positive, that means the reaction is non-spontaneous. But if a reaction is non-spontaneous, what does that tell you about the reverse reaction? The reverse one is spontaneous. So notice, if I tell you delta G for a reaction's positive, you could say that means the reaction's non-spontaneous, or you could say that that means it's spontaneous in the reverse direction as well. Either way, both be true. And what's true if delta G actually equals 0? Reactions reached equilibrium. Awesome. So this is why people originally came up with the idea of delta G. I mean, they derived it mathematically, but the idea was by simply knowing the value of delta G, you automatically know if the reaction is spontaneous or not. Cool. They call it Gibbs Free Energy. Not because it's like free, you know, like going to a sale and getting something free. Question?
Maybe I missed it. Does that also mean that if delta G is negative, the reverse would be non-spontaneous?
That totally is true as well. If delta G is negative, it means the forward is spontaneous, but that also implies that the reverse would be non-spontaneous. Totally true both ways. So Gibbs Free Energy, it's not free because it doesn't cost anything, but free meaning available. Like you free Saturday night kind of a thing, you know? In this case, it's the energy that is available to do work. It's the energy that is available to do work. So let's get a little egocentric for a minute. Let's pretend that I'm the universe, right? So I'm the universe. So, or at least I'm a system, let's say. Maybe not the whole universe. I'm a system. And if I told you, you know, that right now I've got like 500 kilojoules of energy. And if tomorrow you found out I only had 400 kilojoules of energy, well, then you'd know I lost energy. And things tend to lose energy. If I lost energy, it's because I used that energy to do something, to do work. And that's what we normally expect. So, but if I told you that, you know, I started out with 500 kilojoules of energy right now, and tomorrow I had 600, you'd be like, where'd you get it? Because things don't just naturally get more energy. They have to get it from somewhere. But things will naturally perform work. So if I ended up with more energy, I didn't do anything tonight, right? I was relaxing. I was, you know, mooching off somebody, getting some energy from somewhere. But when I actually do work, then I lose energy in that case. And so in this case, it's the energy that's free or available to do work. And that's why when the system loses energy, it's because it did some work. And so that's the kind of process that is spontaneous. So if I let go of this marker, where's it going to go? Down. Gravity propels things downward. So, and conveniently, it starts with a G. Delta G, I want it to be negative. I want the change to be going down. It's a decrease in Gibbs free energy for a spontaneous process. Questions? Okay. So, I just want to let you guys know that I saw the scores on your last exam, and you guys need to get higher test scores. You guys are like, really? Did you just say that? So, okay, maybe not really. But I did not actually see your exam scores, but you need to get higher test scores. So it's just my little convenient way of remembering this lovely equation. I say it's mine. It's in a lot of books. So, but get higher test scores. So your way of remembering this fundamental relationship. So delta G, delta H, and delta S are all related to each other. Now, which one of these actually tells you if a reaction is spontaneous? Delta G. Delta H by itself won't tell you that. Delta S by itself won't tell you that. But delta G will tell you if a reaction is spontaneous or not. Cool. So through this lovely relation, we can actually go through and talk about some different scenarios of when delta H and delta S are positive and negative, and under what conditions that kind of a reaction might be spontaneous. So and that's what we're going to look at next here. So before we get into this, though, to make sure you're ready to do this, I got to make sure your math skills are up to par. So if you add a positive number to another positive number, what are you going to get? Positive number, awesome. You guys are in good shape. If you add a negative number and another negative number, what do you get? Negative number, awesome. If you add a positive number and a negative number, what do you get? It depends on whichever one has a greater magnitude. That's pretty much what you needed to know math-wise to talk about what we're about to talk about here. So in this case, we're going to talk about delta H and delta S, and whether or not they're positive or negative. So, and we're going to talk about this in a conceptual sense, but then we're also going to go and talk about it in a mathematical sense. You need to know it one way or the other. So if we look here, we're going to split this up into two terms. Delta H is the first term, and the second term is going to be the negative T delta S. Temperature has to be in units of what? Kelvin. Can that ever be negative then? No, so that's always positive. And so in this case, whatever the sign on delta S is, this second term, because that negative sign right there, will have the opposite sign. So it turns out, first thing we'll look at, that the universe wants delta H to be negative, and the universe wants delta S to be positive. Now I say that's what the universe wants, and that's just the universe wants anything. So, but that's what I'm saying. The universe wants that, at least in this case, the universe wants that for a reaction to be spontaneous. If you give the universe what it wants, the reaction will be spontaneous. Now we can look at that mathematically for a sec here. If delta H is negative, so if delta S is positive, then this entire second term will be negative. And so in this case, what do you get when you add two negative numbers? A negative number. And so in this case, under these conditions of delta H being negative and delta S being positive, delta G has to come out negative. There's no way around it. And so in this case, we look at how temperature plays a role here. Temperature can make this second term, in this case, a big negative number or a small negative number. At low temperature values, this would be a small negative number. At high temperature values, this would be a big negative number, right? So, but no matter what, whether it's a big negative or a small negative, I'm still adding two negatives, and delta G will come out negative no matter what. And so in this case, we say that this reaction will be spontaneous at all temperatures. Spontaneous at all temperatures. Now, we talked about this a little bit earlier in the second law of thermodynamics. For a spontaneous process, the delta S of the universe is positive. Well, here we're just talking about just the system. All these terms apply just to the system, not the surroundings. So it's not the entire universe. But it turns out if the delta S of even just the system is positive, that's helping the reaction, you know, it's helping give the universe what it wants. And kind of halfway there, if you will. So it turns out, if you look at delta H deals with giving off energy or absorbing energy, heat, right? And so in this case, what does the universe want? Well, the universe wants what every girl wants. A stable guy, right? So girls like stable guys, you know? If you know there's going to be a girl at a party, so, and you, what do, guys? You try and act all cool. Like, you probably look stupid doing it, like, I'm cool. Cool. I'm really cool. So what you don't do is you don't drink a little too much and make a complete fool of yourself and who wants to fight? Who wants to fight? Come on! You don't do that because the girl's going to think you're a total whack job. She's not going to like you no matter how cute you are, right? So girls like a stable guy. Well, the universe likes things to be stable as well. And it turns out what that means is when you're low in energy and cool, you're more stable. The universe likes things to be more stable. So in this case, does the universe want a reaction to give off heat or absorb heat? To give off heat. Because if you give off heat, then you'll have less energy. And if you have less energy, you're going to be more stable. And so that's what the other half of what the universe wants. The universe wants a reaction to give off heat because the products will end up more stable as a result. But the universe also would like it if the system gains disorder. So stable and messy, that's what the universe wants. And if you give the universe what it wants, the reaction will be spontaneous no matter what temperature you do it at. So let's say we do the exact opposite. Let's say we have the system gain energy, gain heat, endothermic, and we have it actually get more ordered. It loses entropy. In this case, delta H is positive, and if delta S is negative, then this second term is going to be positive. And now, no matter what value for T I plug in, whether it's a low temperature or a high temperature, I'm adding two positive numbers, and delta G will have to come out positive. And so this reaction, regardless of temperature, is going to be non-spontaneous. And so we say non-spontaneous at all temperatures under those conditions. Okay, the last two here. The last two here are going to demonstrate the temperature dependence. When delta H and delta S have the same sign, that's when the reaction will only be spontaneous above or below a certain temperature. Can anybody remember a process that we went over earlier where delta H and delta S were both negative? It's one of the phase changes. And there's three choices here. Where delta H and delta S were both negative. When you freeze something, when a gas condenses, or when you have vapor deposition. Delta H and delta S are both negative. When is freezing spontaneous for a compound? When it's cold, right? And cold's a relative term, right? You know, like my sister thinks 84 degrees is cold and needs a blanket, whereas I'm like sweating at 84 degrees, so it's relative. It's also relative for all reactions. When we say, in this case, like when delta H and delta S are negative, we're going to say it's spontaneous at low temperatures. And by low temperatures, we just mean it's only spontaneous below a certain maximum temperature. Only spontaneous below a certain maximum temperature. Somebody named for me one of the phase changes where delta H and delta S were both positive. So endothermic and increase in entropy. Fusion, melting, what else? Vaporization, boiling, awesome, and sublimation. And when are those processes spontaneous? High or low temperatures? Only high temperatures. Notice water's only going to boil above 100 degrees Celsius. Ice is only going to melt above 0 degrees Celsius. So when we call something high or low here, it's kind of relative because notice you wouldn't probably consider 0 degrees Celsius a high temperature, but ice does. And it's not what you think, it's what ice thinks when we're talking about melting ice. It thinks 0 degrees Celsius. Anything higher than that is high enough to melt it. Okay, so we know an example, or at least a few examples of each of these, but let's talk about it conceptually for a minute. So if delta H is negative and delta S is negative, well, then this first term is negative. But if delta S is negative, then this second term is going to be positive. So in this case, in which of these terms is the universe getting what it wants? Delta H, that's what the universe wants. The universe doesn't want a reduction in entropy, but this is what the universe wants. Which term, the delta H term or the delta S term, is temperature a part of? Delta S. And so because temperature is multiplied by delta S, if this isn't what the universe wants, then minimize the damage by putting a small value of T there. But if this is what the universe wants, then let's amplify that and make it as high a temperature as we possibly could to make that a very large term. And that's kind of the strategy here. So in this case, delta H is what the universe wants. Delta S is not what the universe wants. And so in this case, let's minimize the damage of delta S here and make it only spontaneous at low temperatures, small values of T. So if you look at the last one, where delta H and delta S are both positive. So delta H is positive, but if delta S is positive, then this second term will be negative. And so in this case, you can look at it here and see, yeah, the negative is what we want for a spontaneous reaction. This term is good. This term is bad. In this case, I want this term to be the dominant term. And so what do I want to do? Plug in a big value for T. And that's why when delta H and delta S are both positive, spontaneous at high temps. So I tried to kind of look at this conceptually, maybe kind of facetiously, of what the universe wants. We've looked at it mathematically. And a lot of students just simply memorize this chart. But one way, shape, or form, I don't care if you memorize the chart or are able to recreate it mathematically or conceptually, but one way, shape, or form, you need to know this. So usually half the students will memorize this and half the students will be able to derive it one way or another. So take your pick, but you do need to know this. Any questions before we move on? Cool, let's do a couple of example questions with this real quick. This is right off your handout here. So here, A gas plus B gas goes to C gas, and delta H is negative 25 kilojoules per mole. And essentially I'm asking you, is this reaction spontaneous at all temperatures, not spontaneous at all temperatures, spontaneous at low temperatures, or spontaneous at high temperatures? Which of these categories does it fall into? Well, in this case, what do you know about delta H? It's negative, so you should have it already narrowed down to two options, right? In this case, with delta H being negative, it's either spontaneous always at all temps, or it's only spontaneous at low temps. It's got to be one of those two. Well, what's delta S for this reaction? How do you know it's positive? Do you know that it's positive? How do you know it's negative? Good, it wasn't given, but how should you know that it's negative? Yeah, 2 moles of gas to 1 moles of gas. The biggest thing, again, to look for, change in moles of gas. Decrease in moles of gas is definitely going to be a decrease in entropy, a negative change. Cool. And so, now that I know that delta H and delta S are both negative, when is this reaction spontaneous? At low temperatures. Awesome. Typical type of question on this particular concept that you'll get on this exam. So one more. Give you this reaction here. If I tell you that this reaction is only spontaneous above 2000 Kelvin, at temperatures above 2000 Kelvin, then what could you tell me about this reaction? If it's only spontaneous above 2000 Kelvin, then you should be able to give me the sign of both delta H and delta S. If it's only spontaneous above 2000 Kelvin, then where are we falling here? Yeah, plus plus. Delta H and delta S are both positive because they're only spontaneous above a certain temperature, above a certain minimum temperature, spontaneous at high temps. So this lovely equation here, delta G equals delta H minus C delta S. And again, how do you remember this thing? Awesome. So you can use this equation under standard or under non-standard conditions, but most of the time you're going to see this thing showing up under standard conditions. Now here's the deal. Delta G, standard, depends on temperature then. So depending on what temperature you're at, you could have a different standard value. And technically, 25 degrees Celsius is not really part of the standard conditions. But delta H and delta S, we usually assume those are fairly temperature independent in general chemistry. In a physical chemistry course, all this gets way more complex, and we'd have more equations. But for Gen Chem, we just assume these are pretty constant over a given temperature range. But delta G changes. Let's say you're doing a phase change. If I have water at 50 degrees Celsius, what phase is it probably in? Liquid. So, and if I have water at 150 degrees Celsius, what phase is it probably in? Gas. But if I have water at 100 degrees Celsius, what phase is it in? It's not right between, well, sort of, but it's in equilibrium between both. And if at the phase change temperature, two phases are in equilibrium, then delta G at that point must be 0. And so here's where things get tricky, is if we had equal amounts of equal moles, 1 mole, if you will, or 1 molar concentrations anyways, of steam and liquid water, the question is when would delta G standard, at what temperature value would delta G standard be 0, so that under standard conditions at that temperature it would be at equilibrium? Well, then we just plug in 0 and rearrange this equation. And so you'll find oftentimes another equation is given. So, and they usually just rearrange this and they say that delta S standard equals delta H standard over T. And this is true at specifically the phase change temperature. Only true at the phase change temperature. And so notice there's 3 things in this equation now. If I give you 2, I can say solve for the third one. If I give you delta S and delta H of boiling water, then I could say what's the temperature at which water boils? What's the phase change temperature? So notice if it's water though, you should just like skip it, right? And just say 100 degrees Celsius, 373 Kelvin, because you know that one. But if I do it for like benzene or ethanol, you may not know that one, you'll have to calculate it. One other thing to note, just like delta G, what units do we usually give you for delta H? Kilojoules per mole. But what units do we usually give you for delta S? Just joules per Kelvin, it turns out. So kilojoules, joules per Kelvin. And so you got to make sure your units match there if you're going to do a calculation as well. Units are really important in this chapter, if you haven't noticed. Cool. One other thing about this, if you recall, when delta H and delta S had the same sign, both positive, both negative, you might get a question that gives you delta H and delta S, and let's say delta H and delta S were both positive. When's that reaction spontaneous again? High temperatures. And what if I gave you delta H and delta S values, they were both positive, and I said, what is the minimum temperature at which this reaction becomes spontaneous? Well, the minimum temperature, you'd actually calculate it the same way. Because when delta G is positive, it's not spontaneous. When delta G is negative, it is spontaneous. What's the crossover point from getting a positive delta G to getting a negative delta G? What's the crossover point? When delta G is 0. And so if you plug in 0 for that case as well and solve for T, another way to solve for T, the threshold temperature above which or below which a reaction becomes spontaneous. So another similar type calculation for this. Say that one more time. Yeah, so if I gave you a delta H and a delta S and they were both positive, and then I said, above what temperature would this reaction become spontaneous? You'd actually use a very similar expression here. You're going to plug in 0 for delta G and just solve for the T value. Plug in the delta H, plug in the delta S, and solve for T, which essentially this equation comes from that particular situation. So another place you'd use it besides just phase changes.
How do you know if it's going to be above that temperature that you solve for or below?
Well, again, if delta H and delta S are both positive, when's that reaction spontaneous? High temps, which means above a certain minimum temperature. But if delta H and delta S are both negative, when's that reaction spontaneous? Low temperature, so below a certain maximum temperature. Exactly. They got to give you the values so you can do that calculation.